Hi, in this video, I'm starting section 3.4. So I'm going to cover this section in two parts. This is a longer section. So 3.4, we're going to continue with polynomial functions. We're going to see what the graph looks like, what the graph of polynomial looks like, some applications, and models involving polynomial functions. So I'm going to start first with a variation of the basic functions with it. We will consider first f of x equal x to the n power. So we're going to see what happens if n is odd. That is, when the power is either 1 or 3 or 5 or 7, and so on. So I'm using a graphing calculator for that. Okay, so I'm using this graphing calculator. We're going to see what happens when the power is an odd number, like when the power is 1. X to the first power is x, or x to the third power. That was one of the basic functions, or x to the fifth power, x to the seventh power, and so on. I'm going to do one more, x to the ninth power. So as you can see, the behavior is very similar to x to the third power when the power is odd and greater than 3. It's very similar to x to the third power, but the turn becomes steeper. As it approaches the origin, the turns become steeper. But it levels off as it approaches the origin, and once it moves away from the origin, it turns faster. I mean, the increase becomes faster. So I mean, well, I said steeper, actually it becomes flatter as it approaches the origin. And they all have 3 points in common: -1, -1, 0, 0, and 1, 1. Okay, so if n is odd, the domain and range are both all real numbers. And the function is increasing over its entire domain. Now let's see what happens if n is even. If n is even, that is when n is 2 or 4 or 6 or 8, and so on. Well, even and positive. So we're not going to include 0. That the function identically 0, so that's not very interesting. So let's start with x squared. So that's a function we spend a good amount of time on. Then x to the fourth, the behavior is similar to x squared, but as it approaches the origin, the turn is going to be sharper, and it becomes flatter as it approaches the origin. That pattern continues as the value of n increases. And they all have 3 points in common: -1, 1, 0, 0, and 1, 1. So if n is even, the domain is all real numbers. And the range is 0 to infinity, including 0. So that's bracket 0, infinity. So the function is decreasing over -infinity to 0, or we're just going to include open intervals. We're not including the 0, and increasing over 0 to infinity. Okay, so let's see it again. So the domain is all real numbers. The range is 0 to infinity, including 0. And it's going to be decreasing from -infinity to 0 and increasing from 0 to infinity. Okay, so I'm going to show you the properties of the graph of x to the n. So I'm going to copy that. That's on page 339. As with quadratic functions, the absolute value of a in f of x equals ax to the n determines the width of the graph. When the absolute value of a is 1, the graph is stretched vertically, making it narrower. When the absolute value of a is greater than 0 but less than 1, the graph is shrunk or compressed vertically, making it wider. And you also have reflections. When a is negative, the graph is going to be reflected across the x-axis. So I'm just going to copy this part. That's on the next page. Compared to the graph of f of x equals ax to the n, the following also holds true, or hold true. The graph of the opposite of a, x to the n, is reflected across the x-axis when a is positive. The graph of f of x equals ax to the n plus k is going to be shifted k units up if k is positive, and absolute value of k units down if k is negative. So we did these transformations before. Then the graph of f of x equals a times x minus h to the n is going to be translated h units to the right if h is positive, and absolute value of h units to the left if h is negative. And the last line, if we apply all the transformations, we have a combination of these translations. And if a is negative, the graph is also going to be reflected. Okay, so I'm going to go over example 1. We are going to graph each polynomial function and determine the largest open intervals of the domain over which each function is increasing or decreasing. So if we start with number 1, with part A, f of x is x to the 5th minus 2. So the graph of x to the 5th we know that 5 is an odd number. So the graph of f of x equals x to the 5th is going to be similar to x to the 3rd. It's going to be increasing. It levels up as it approaches the origin, and then starts increasing at a faster rate again. So this graph is going to be, we only have one transformation. So that's going to be shifted 2 units down. The graph of x to the fifth passes through three. We know 3 points on the graph of x to the fifth, which are -1, 0, 0, and 1, 1. But this was shifted 2 units down. So to have an idea, this not turning point, but this point that acts like the origin is going to be 0, -2. And then the graph, instead of passing through 1, 1 is going to pass through 1, -1. And instead of passing through -1, -1 is going to pass through -1, -3. So that's an idea of the graph. And they were asking us, determine the largest open interval of the domain over which each function is increasing or decreasing. So this function is increasing over -infinity to infinity. So I'm writing that. So this is increasing over -infinity to infinity. Number 2. Now f of x equals x plus 1 raised to the 6th power. So we have the basic function, or the function we are comparing to is x to the 6th, and x plus 1 is going to involve a shift, a horizontal shift, in this case, to the left. And 6 is an even number. So x to the 6th is going to behave like x squared. It's going to be decreasing from -infinity to 0 and increasing from 0 to infinity. Well, x to the 6th. X plus 1, there's going to be a shift. So those intervals are going to change. Okay, so now that we have that, the graph of x to the 6th is shifted or translated 1 unit to the left. Okay, so that's going to be shifted. So instead of 0, 0 is going to pass through 0 or through -1, 0. Instead of 1, 1, it's going to pass through 0, 1. And instead of -2, or instead of -1, 1, it's going to pass through -2, 1. So the domain and range are going to be the same. The domain is -infinity to infinity, and the range is 0 to infinity. But the intervals where the function is increasing or decreasing have changed. This is decreasing over -infinity to -1, and increasing over 1 to infinity. Or -1 to infinity. And part C, f of x, well, we have this function. We're going to describe the transformations and determine the largest open interval of the domain over which the function is increasing or decreasing. So in part C, the function is -2 times x minus 1 cubed plus 3. Okay, so the graph of x cubed is vertically stretched by a factor of 2. It's going to be reflected across the x-axis. And it's going to be shifted 1 unit to the right and 3 units up. That's 3 units up. Okay, so let's see the graph. We start with the graph of x minus 1, or the graph of x cubed. So 3 is odd. Is going to be, well, and that was one of the basic functions that we did in section 2.6. But a few things are happening. First, that the graph shifted 1 unit to the right and 3 units up. And it was vertically stretched by a factor of 2. So we have this point. Also, the graph was reflected. So instead of going through 0, instead of going through 0, 5 or instead of going through 0, 1, is going to go through 0, 5. And is going to pass through 2, 1. Okay, so instead of 1, it's going to be 2 because it was vertically stretched and the graph was reflected. Remember the original graph? The graph of x cubed is something like this. And it passes through 0, 0, -1, -1, and 1, 1. So the new graph passes through 0, 5, 1, 3, and 2, 1. So this is an idea of the graph. And finally, the graph is decreasing. It's never going to be increasing. It is decreasing. Over -infinity to infinity. Okay, so far we have done the most basic polynomial function, x to the n. We have seen some of the transformations. We did these examples. So you want more detailed graph, there we have them. So unless otherwise restricted, the domain of a polynomial function is the set of all real numbers. Polynomial functions are smooth, continuous curve. Smooth means that you don't have any sharp turns. Continuous curves on the interval -infinity to infinity. And the range of a polynomial function of odd degree is also the set of all real numbers. Maybe I should copy that. Yeah, so the domain is going to be the set of all real numbers. If the polynomial is odd, the range is also going to be, or if the degree of the polynomial is odd, the range is also going to be the set of all real numbers. So I'm going to go over some of the examples that they have in the book. They are good examples, so I'm going to go over those graphs. Okay, so these are on page 341. So I'm going to go over this figure, figure 25. So the graphs in figure 25 suggest that every polynomial function of 4th degree, there is at least, or is at least one real value of x that satisfies f of x equals 0, or that it only has 1 0. The real zeros correspond to the x-intercepts of the graph and can be determined by inspecting the factor form of each polynomial. So I'm not going to show you where the polynomials are coming from. I'm just going to go over these graphs. So I'm going to write the equations again, because this baby blue is hard to see. Okay, first graph. All these are on page 341. The formula for this polynomial is f of x, f of x equal to 2x cubed plus 8x squared plus 2x minus 12. So this is a polynomial of 3rd degree. And in factor form, this is the exact same as 2 times. So remember, the leading coefficient is going to be the same. 2 times x minus 1 times x plus 2 times x plus 3. So we learned in the previous section that the zeros are 1, -2, and -3, and there are zeros of multiplicity 1. So this is just the exact same function, but it's in factor form. Okay, so this function has real zeros at -3, -2, and 1. And you can see how the graph crosses straight. It passed through -3, 0, -2, 0, and 1, 0. And also the y-intercept, you can quickly see that is -12, either from the formula or from the graph. Number 2, or part B, the second graph in this page. So I'm going to show you the graph and I'm going to write the formula. Okay, so the formula for this function is f of x. In general form is the opposite of x cubed plus 2x squared minus x plus 2. The leading coefficient is -1, and in factor form, this polynomial is the same as x minus 2. If you notice, it only crosses the axis, it only crosses the x-axis once, and it has 3rd degree. The other zeros are going to be complex. And we saw in the last section that complex zeros come in conjugate pairs. So are going to be the opposite of I and I. So we can see that it crosses straight at 2, 0. And this graph has 1 real 0 at 2. If the 0 has multiplicity 1, we don't write that. See? In part C, I'm going to copy the graph and write the formula. Okay, the formula for this function is f of x equal to, in general form, this is x to the fifth plus 4x to the fourth plus x cubed minus 10x squared minus 4x plus 8. So that's in general form, and in factor form, this is x minus 1 squared times x plus 2 cubed. You can see from the graph that it has two real zeros. But at -2, 0, the graph behaves like the graph of x to the third power. As it approaches -2, 0, it levels off and then starts increasing again. And at 1, 0, it behaves like x squared. So it touches the axis but doesn't cross it. So the graph has real zeros at -2 and 1. At -2, it has a 0 of multiplicity 3. Because you have x plus 2 to the third power, and the graph also, you can tell from the behavior of the graph that it levels off and then crosses. And at 1. At 1, it has multiplicity 1. You have x minus 1 squared, and you can see that the graph touches the axis but doesn't cross it. Okay, so these were polynomials of odd degree. And they have one thing in common, that the range is going to be all real numbers. The first one continues to fall to the left and rise to the right. The second one continues to rise to the left and fall to the right. And the third one continues to fall to the left and rise to the right. The next two graphs are examples of polynomial of odd degree. So I'm copying the graph. And I'm going to write down the formula. The formula for the polynomial with this graph is x to the fourth minus 5x squared plus 4. In factor form, this is x minus 1 times x plus 1 times x minus 2 times x plus 2. So that's a polynomial of even degree, and you can see that it keeps rising to the left and to the right. This polynomial has 4 real zeros of multiplicity 1. So f has 4 real zeros. At, in order, that's -2, -1, 1, and 2. And the last graph is another polynomial of even degree. Okay, so I'm copying that graph. Okay, so the formula is f of x. That's a polynomial of 6 degrees. And you can see that the degree is even, and it continues to fall to the left and fall to the right. But this is the opposite of x to the 6th minus x to the 5th. Plus 4x to the 4th plus 2x cubed minus 5x squared minus x plus 2. That's in general form. And in factor form, this is the opposite of x plus 2 times x plus 1 squared times x minus 1 cubed. So it has 3 zeros. -2 is a 0, the graph crosses straight. -1 is a 0 multiplicity 2. You have it to the second power, so the graph touches, but doesn't cross. And 1 is a 0 multiplicity 3, so the graph levels off and then continues to decrease. Levels off and then crosses. Okay, so let's summarize that. This has 3 real zeros. So f has real zeros at -2, at -1, it has 0 multiplicity 2, and at 2, at let's see, at -1 and at 1, it has 0 multiplicity 3. Okay, so let's summarize the behavior as zeros, and also what the degree of polynomial tells you about the behavior of the graph. Yeah, actually, the book doesn't have that, so I'm just going to type it. Okay, so the multiplicities tell you how the graph behaves. So if the polynomial function has a 0 multiplicity 1, the graph crosses the x-axis. If it has 0 of even multiplicity, not necessarily 2, but it can be multiplicity 4 or 6 or 8, and so on. If f has a 0 of even multiplicity, the graph intersects but doesn't cross the x-axis. And number 3, if the graph has a 0 of all multiplicity greater than 1, the graph levels off and crosses the x-axis. And the book shows you a graph. What happens is it's a 0 multiplicity 1 is going to cross. If it has a 0 of even multiplicity, the graph is tangent to the axis, so that is the graph bounces or turns at C. And the graph crosses and is tangent to the x-axis, it sees a 0 of all multiplicity greater than 1. So the graph wiggles at C. Okay, so we have some information about the degree, the degree. So we know the behavior at the zeros, but also the degree tells you something about the number of zeros or the intercepts. So that's going to be the last thing. Okay, so I'm looking for the part of the turning points. I don't know if the book has that. Oh, yes, there it is. So I'm going to copy it. And let's write a note. So a polynomial function of a polynomial function of degree n has at most of degree n. Has at most n x-intercepts or n zeros. I should write this as notes. So that's the first note. Has at most n zeros, which can be real or complex. And number two, the sum of the multiplicities of the zeros equals the degree of the polynomial. Whether the zero is even or odd, it's going to be the sum. Like some of the examples we did, like this one, that's a polynomial of 6 degree. The multiplicities are 1, 2, and 3. So the sum of the multiplicities is 6. That one is a polynomial of 4 degree. So the sum of the multiplicities is 4. Then this one is a polynomial of 5th degree. The sum of the multiplicities is 5. Polynomial of 3rd degree. 2 of the zeros are complex conjugates. So the sum of the multiplicities is 3. It's 1 plus 1 plus 1, so it's 3. And the first we did was a polynomial of 3rd degree. The sum of the multiplicities is 1 plus 1 plus 1. And the turning points, that's going to be the last thing I mentioned in this video. So a polynomial function of degree n has at most n minus 1 turning points. It can have less, but it cannot have more than n minus 1 turning points, with at least one turning point between each pair of successive zeros. So let's go back. I'm going to go back from the beginning. Okay, so the first one. So that is a polynomial of 3rd degree, and it has 2 turning points. So it has 1, 2 turning points. So these are the turning points. The second example is a polynomial of 3rd degree, so it also has 2 turning points. So it's, these are turning points. You can see that one is slightly below the other one, so it does have 2 turning points, and it's a polynomial of 3rd degree. The third example is a polynomial of 5th degree, so it has only 2 turning points. So a polynomial of 5th degree is going to have at most 4 turning points, but it can have less than that. This one is a polynomial of 4th degree, and it has 3 turning points. And the last graph is a polynomial of 6th degree, but it has 3 turning points. It cannot have more than 5, but it can definitely have less than 5. Okay, so this is it. Thank you for listening. I will continue with this section in the next video.